Okay, so
Good morning.
good morning. So you have
Good
to say
morning, sir.
good morning. Why people the strength student strength is less? I have not conducted any other meeting. No, only one meeting I have opened. I think. Okay, let the students get joined. For a time being, we will just start with the. Okay, so in the last class we were discussing about the zero crossing detector, and so in the some of the applications with respect to the positive feedback. So we know that positive feedback as well as negative feedback. So we can employ for an operation amplifier, we can employ so positive feedback as well as negative feedback. So whenever you're going to use the operation amplifier in the negative feedback configuration, so you can able to control the gain as well as you can able to control the output. So control the output as well as so the output will become proportional to that of input. That means it is going to linearly change with respect to input signal. So whereas when you employ the positive feedback configuration of the op amp, so we can see since the output will be given to the non-inverting terminal. So in the inverting configuration, so the output of the op amp will be given to the inverting terminal. So it is going to employ through the feedback network, it will be given to the inverting terminal. So we can say that the op amp is said to be configured in negative feedback configuration. When in the negative feedback configuration, so we have seen the inverting, non-inverting as well as voltage follower configuration. So these are the three different configurations which are going to be seen in the inverting along with the differential amplifier configuration. And also in each of the configuration we have seen the application like summing, scaling as well as averaging amplifier for both some inverting amplifier, non-inverting amplifier as well as voltage follower. And based upon that we have seen the these are the three some fundamental applications with respect to the negative feedback configuration. So after moving, we started with the open loop configuration of op amp. So in open loop configuration, that means whenever op amp is not employed with any feedback, or when you employ the op amp with the positive feedback, so both will be considered the same. So that type of circuit applications, so you'll be getting for switching type of application. So the output of that op amp will be either in two of the saturation voltage. So one will be in positive saturation, one will be in positive saturation, or another will be in the negative saturation. That means the output will vary between the plus Vsat and minus Vsat respectively. So this type of, irrespective of this type of signal, so irrespective of the type of signal as well as the waveform shape, so you'll be getting the square wave as a output. So square wave, why you will be getting square wave? Because since you employ the positive feedback, so there is no purpose of showing this square wave. But the thing is that so the gain will be very much high, that it will be greater than that of it will be greater than that of the maximum power supply for that operational amplifier. So we know that according to 741 op amp, so we can give maximum power supply up to plus or minus 30 volts. Right. So when we are going to give only plus or minus 30 volt supply, then the maximum output voltage is also going to be limited. Right. So the maximum output voltage for that applications will be 1 volt less than that of the maximum power supply. So plus or minus 30 means plus or minus 29 you will be getting. That means if you connect an oscilloscope, or if you connect any if I want to measure in CRO, so oscilloscope and all. So if I connect the input signal as well as output signal, if you are going to keep, so you'll be getting the square wave. So why you will be getting square wave? Because within a fraction of second, so it will enter into the saturation, indicating that the output will be very much higher compared to that of the maximum output voltage limitation. So it will be having greater than that. So the op amp will get saturated in this particular direction. So if it is moved to the negative value, maximum negative value, then it will be maximum negative. It will be displayed on the CRO screen will be plus Vsat and minus Vsat, so that you will be getting the square wave as the output. So this is the one of the important applications. So when you are going to have this type of application, so this type of application can be utilized for switching applications, as well as you can able to generate the duty cycle. So duty cycle is very important whenever we are going to work in any of them. So in timer circuits, as well as in laptops, as well as computers and all, you can see. So for how much speed, the operating frequency and all, we are going to be dealing with. So in that particular application, as I already mentioned in the oscillator, when I was doing in the oscillator, so it has to provide a sustained oscillation. So sustained oscillation, and it has to be provide a particular duty cycle. It should not vary the duty cycle. In the sense, the time period of the waveform should not vary. And here in the crystal oscillators and also you will be getting a sustained accurate oscillation. Okay, that will be provided by the crystal oscillator. So because of that, so I just told in all the digital application, digital circuits and all. So we are going to obtain the clock frequency based upon the crystal oscillator frequency will be treated as a clock frequency. Even in microcontroller also you might have studied. So 11.0592. So that is the frequency, megahertz will be the frequency of the microcontroller. So that is the oscillation frequency. That is the oscillator frequency. So that is also going to be generated from the crystal. So similarly, so various properties I have also studied. So depending upon that, it is going to provide a sustained oscillation, and it is not going to vary with respect to temperature or if, with respect to any component value. So because it is a crystal, and correspondingly, so based upon the piezoelectric property, as I told, so it is going to work and it is going to provide a sustained oscillation. So the same way here, the using of this operational amplifier in a positive feedback. So in a positive feedback also, it is going to generate a duty cycle. So we are going to generate a time period, so which is going to have specific duty cycle. So this specific duty cycle can also be varied. So based upon the feedback component resistance value. So based upon that feedback resistance value, if you change, so you can change the on time as well as off time. Whereas, so it is going to have for a given particular input signal waveform, so you will be getting the perfect output depending upon the resistance value. So you can able to change. So if I want to have a 50% duty cycle, then I can have some equal resistance to be connected over here. So in this case, just explain the zero crossing detector and all. So in the zero crossing detector, if you find the duty cycle as well as if you find the input and output waveform, so you can see as and when, so the input sinusoidal waveform crosses the zero, so above or below, you can see the output is going to switch from one saturation to another saturation. So that if you consider the time duration, so the time duration for the input as well as output will be exactly same, and you can see the on time. So this is nothing but a duty cycle. So there is a on time as well as this is nothing but a off time. So whenever the duty cycle, if you consider the 50% of the time it is going to be on, and 50% of the time it is going to be off. So it is going to have a 50% duty cycle. So this zero crossing detector, if you connect one side, so some of the applications in ICs within the IC. So if I want to have a 50% duty cycle, means either I can use this circuit, zero crossing detector circuit, and can generate a square waveform, because this square waveform will be useful for all the other, because it is a very important very important applications. Okay, so in the case of oscillator also, we are going to use the oscillator clock frequency for all the internal circuits. So it is going to provide with the same oscillator, so that all the signals, all the digital circuit inside the IC will be correlated with the oscillator so frequency, so that the rise time, fall time and all, it is going to be dependent only on the oscillator frequency for all the digital circuit within the IC. So this oscillator, it is going to generate the clock signal. So based upon that clock information only, all your microcontroller also, you can see all the microcontroller application instruction by say instruction which is going to execute everything, it is going to be dependent on the oscillator frequency. So that oscillators plays a major role. Whether you're going to for a read or write cycle or any of the execution part and all, so this circuit or within the microcontroller IC, so it is also dependent on the oscillator. So for that very important. So this is it is going to have only two outputs. So this will be used for switching type of applications. Only switching, because in this case you can see positive saturation as well as negative saturation. Only two output will be getting, irrespective of what type of waveforms you will be giving. So output will be in only in two states, either in positive saturation or in negative saturation. Hence, this type of applications will be called as a switching type of application. So this is about the zero crossing detector and inversing zero crossing detector as well as non-inverting zero crossing detector. And we have started with the Schmitt trigger. Schmitt trigger is a special case of zero crossing detector. So the importance of this Schmitt trigger is, so you can vary the duty cycle. So you can vary the duty cycle, and the circuit for the Schmitt trigger is being represented over here. So we will be having operational amplifier, and the circuit. If you look at a first stage, if you look, so this circuit will be resembling like a non-inverting amplifier configuration with the input terminal will be given to the inverting terminal, and for output will be given to the non-inverting terminal. So only difference is these two. So if you interchange the input terminals, and if you write the non-inverting amplifier circuit, so the circuit is going to work as a Schmitt trigger. So this is inverting Schmitt trigger, and if you see the circuit, so forget about this inverting and non-inverting for the time being. So if you are going to provide an input, and you are going to have an output to be developed across R2 and R1, and the voltage across R1 will be given as a feedback to the one of the input. So if I interchange these two plus and minus, the circuit is going to work like a non-inverting amplifier. So now that's why very important. So whenever you're going to draw the circuit and all in lab exam or in theory exam also, so the terminals what you are going to write and what you are going to give it as a feedback is plays a major role. So anything if you give from the output to the non-inverting terminal will become this as a positive feedback. So now here also you can see the output voltage is developed across R2 as well as R1. So complete output voltage is across the load resistance RL. At the same time, it is also developed across R2 and R1 because it is the same voltage drop. So if you see the voltage drop across R2 means, so we need to say, so V naught into R2 divided by R1 plus R2, that is the voltage drop across R2. At the same time, if I want to know what is the voltage drop across R1, so I should see, so V naught into R1 divided by R1 plus R2. So this is the voltage drop. So this voltage of drop across R1, so that is going to be given as input to the non-inverting terminal. So because of that, so we are going to call it as a we are going to call it as a we are going to call it as a positive feedback. So since the output of the operational amplifier is given as some is fed back to the input to the non-inverting terminal, so the circuit will going to operate like a positive feedback. And since the input has been given to the, so this is the input voltage source. So this input voltage source has been given to the inverting terminal. So this circuit is going to work as a inverting Schmitt trigger. Okay, inverting Schmitt trigger. So this is the circuit, and we have to remember. So this is a very important point. So what is that is? So whenever we are going to see the output voltage, so in a positive feedback function at the initial stretch, you should see. So the output will be, as I mentioned, so in this circuit, in the previous circuit also, so we can see the output will be either in these two states, right? So either it will be in positive saturation, in negative saturation, or it will be in positive saturation. So no other intermediate output will be not having whenever you employ the positive feedback. So the same stage here also when you're going to analyze the circuit. So when you're going to analyze the circuit for the inverting Schmitt trigger circuit, so first thing is that so since you have employed the output is given to the positive terminal, so the output operation amplifier is going to work with the positive feedback configuration. So you should think that it will be in positive or negative saturation. So before that I should see where it will be exactly. So in this case, if you consider V in, so input voltage terminal, as soon as you apply to the inverting terminal, so the input voltage will be zero. So this input voltage will be zero. At the same time, so since the output will be in one of the saturation, so assume it is a positive feedback, right? So it will be in the positive saturated. So assume that for a plus or minus 15 volts apply. So it will be, you will be getting the output voltage to be saturated in plus 14 voltage, because it is the positive feedback. So plus 14 so this plus 14 voltage will be developed across RL as well as the combination of these two feedback resistance R2 and R1. So plus 14. So you will be getting, if the values of resistance R1 and R2 both are equal, suppose 1 kilo ohm and 1 kilo ohm, if I am going to connect it as a feedback resistance R1 and R2, both are 1 kilo ohm, then obviously the voltage will get equally divided across resistance R1 as well as R2. So 7 volts over here, 7 volts over here. So you'll be getting 7 volts as the voltage drop across R1. So when this voltage is given as fed back to the non-inverting terminal, so this is going to be provided with plus 7 volts. So since it will be, since the output will be either in one of the saturation at the beginning, so you will be having a plus 14 means a plus 7 volts you will be having across this across the non-inverting terminal. 7 volts will be greater than so inverting input voltage at the beginning of the stage. So V will be equal to 0, and non-inverting terminal it will be equal to 7 volts. So because of which what will be having, so because of which the output will get saturated in positive direction. So whenever the input is increased above plus non-inverting terminal, till that time the output will be saturated in positive direction only. So you can see during this time, so here he has taken different, okay, so this is a different voltage source he has taken, but so through the characteristics you just assume that whatever I just explained, so that you think, so 7 volts and 7 volts. So till this time, so this is the 7 assume this upper trigger point is 7 volts, so that is nothing but equal value resistance. So here it will, input will be till the input is less than 7 volts, so output will be in output will get saturated in positive direction with 14 volts only. So whenever the input voltage increases above 7 volts, so above 7 volts ಗಿಂತ ಜಾಸ್ತಿ ಆದಾಗ, so inverting terminal, so this inverting terminal voltage will be greater than this non-inverting terminal. As I told, so Schmitt Trigger, zero crossing detector, all whenever the operational amplifier is employed with the open loop configuration or positive feedback configuration, so basically it is going to act like a comparator. So comparator tara compare, it is going to compare the inverting input as well as non-inverting input. So inverting input ಮತ್ತೆ non-inverting comparing the inverting as well as non-inverting input. So which one is greater, so that will correspondingly it will make the output to get saturated in corresponding direction. So since the input voltage source is less than the non-inverting input in the beginning up to 7 volts, so the output will be get saturated in the positive direction itself. So you can see the output will get saturated in positive direction up to 7 volts. So here you just forget about this, so that is about 7 volts you will be getting. So whenever the input exceeds greater than 7, so during this time period, so you can see the inverting input will exceed the non-inverting input value. So because of which it is going to get, since the inverting input is greater, so the output will switch to the negative saturation. So the output will get switched into negative saturation, and until, so you can see, so negative saturation switch out. So one important thing is that, so now the inverting input ಜಾಸ್ತಿ ಆಗ್ತಿದಂಗೆ, so output will enter into negative saturation. So now what is the output voltage? Negative saturation. So negative saturation means what? So 1 volt less than this maximum power supply. So maximum power supply is minus 15. So 1 volt less than minus 14 it will be getting. So now the output voltage is equal to what? So minus 14. So this minus 14 voltage is on there. So what will happen? So voltage drop across R2 and R1, it will be equally divided because we have taken the equal value resistance. So minus 7 and minus 7 it will come. So now the non-inverting input is given provided with minus 7. So instead of plus 7 in the previous stage, now it will be minus 7 respectively. So minus 7 is going to compare with this inverting input voltage now. So now inverting input voltage as soon as it is exists, so minus ಆಗುತ್ತೆ. So minus ಆದಮೇಲೆ, so whenever the input again it will reach greater than minus 7, then only the output will switch. Till that time, so the output, so you can see that this minus 7 is greater than this one, right? So the output will be in a negative saturation only. So negative saturation, and whenever the inverting input exceeds the minus 7 value, so it will be from here to, it will start means 7, 8, 9 and 9, 8, 7, 6, 5, 4, 3, 2, 0, 1, 2, 3, 4, 5, 6, 7. So minus 7 ತನಕ ಬಂತು, ಆಮೇಲೆ minus 7 ಗಿಂತ ಜಾಸ್ತಿ ಆಯಿತು ಅಂದರೆ, so you can see again the output will switch from negative saturation to positive saturation. So till this time interval, so you'll be having the output will be having as a negatively saturated output will be getting. So till this time, so whenever the input exceeds greater than -7, so whenever it exceeds greater than -7, so the output will again move to the positive saturation. So in this way, as long as you give the input to the inverting terminal and with the given circuit, so with the given circuit, so you'll be getting the sine wave as input and the square wave as the output. So this is going to be continuous. So this is about the Schmitt trigger. And coming to the characteristics, if you consider, so this is nothing but hysteresis curve. So hysteresis curve. So in which the x-axis is the input voltage and y-axis is the output voltage. So in this x-axis, if it is considered, so you can see here is a positive input voltage and this is a negative input voltage. So before that, so we will see. So why when which what is the voltage terminal which causes the output to switch from positive to negative saturation. So here, whenever the input reaches greater than this value, right? So at that corresponding terminal voltage, we need to find out. So that will be considered as the trigger voltage. So in this case, we are going to call this as the upper trigger point voltage. And whenever the input reaches or exceeds greater than the this value, so it will switch from negative to positive saturation. So these 2 points, it is going to be repeated. So as whenever it reaches this point or greater than this, so again it will go to negative saturation. And whenever the input reaches this point, so again it will move to the positive saturation. So like this, negative to positive, positive to negative, it is going to cause. So this point will be called as the trigger point voltage. So triggering is nothing but whenever it reaches to this point, so it triggers the output to switch from one saturation to another saturation. So that point is called as a upper trigger point. So this is nothing but upper trigger point, and this is considered as a lower trigger point. So this is about the circuit Schmitt trigger. So why it got the name Schmitt trigger is so you'll be having some trigger point voltage. So based upon the feedback configuration, so it is going to switch the output from one saturation to another saturation. So that is what very important topic is this Schmitt trigger. So in the lab also we are going to study. So this experiment we are going to analyze the Schmitt trigger and we are going to plot the stress curve. So in CRO you can plot and you can see the output and you can also check for the hysteresis. What is the hysteresis? Whether it is a positive hysteresis, negative hysteresis or zero hysteresis and all you are going to verify. So I'll just come over there. So before that you can see. So this point from the upper trigger point, so this is the ring button point. So from this upper trigger point to the next upper trigger point, so you can consider this as a duty cycle. So in this duty cycle you can see the 50% of the time, so the output will be in negative saturation and the 50% of the time, so output will be in positive saturation. So it is called as a 50%, it is going to have 50% duty cycle. And now if we see the hysteresis curve, so you can see along the right side, so you can see another figure. So it is going to have a two trigger point voltage and the x-axis as well as y-axis is there. So whatever the value is there, so it is going to be plotted across the this curve, hysteresis curve. So this is nothing but x-axis as well as the y-axis. So in this case, so the input is going to increase from 0 volts to the maximum possible. So it is going to increase in positively. And the same time, so if I go towards the left side of the voltage, so it is going to increase in the negative direction. So since we are going to have a sinusoidal waveform, so whenever you are going to increase the input voltage in positive direction, so you can observe in this positive direction of the x-axis, and during the negative half cycle of the input, so you can see this is along the negative axis. So x-axis is nothing but input voltage and y-axis is nothing but output voltage. So output voltage from 0 to maximum value, so maximum value will be plus Vsat. So in this positive direction, because we are going to see vertically means it is a positive voltage and negatively along the lower y-axis, okay, from 0 as a reference point. So now as soon as the input voltage starts increasing, so 0, in my case the upper trigger point is nothing but 7 volts. So you can see, so up to 0 to 7 volts, so trigger point voltage until it reaches. So you can see, since it is a positive feedback, So I'm going to start with from 0 input voltage 0, 1, 2, 3, 4, 5, 6, 7. Whenever it comes to the 7 voltage, till that time the output will be positively saturated. Whenever the input just exceeds or it becomes equal or greater than the non-inverting terminal by just 30 microvolts, so the output will switch from positive saturation to the negative saturation. So as you increase the input voltage, so just above 30 microvolts, so you can see the output will switch from positive to negative saturation. And then if you still increase the input in the x-axis, so in the greater than this upper trigger point. So this is the trigger point voltage, wherein which it is going to, whenever it reaches this trigger point voltage, it will cause output to switch from positive to negative saturation. And if you continue the input voltage in the positive direction, the output is also going to be in the negative saturation itself. So that means during this time interval, so from this upper trigger point to this peak of the input, positive peak of the input voltage, you can see this is the input voltage. At the same time, so you will be also getting the output to be saturated in positive direction, and it will move towards here. So now when it comes down the peak of the input signal and up to lower trigger point voltage, so this from here to here it has come, so it will be in this saturation only. After that you can see it will come to 0. So whenever the input voltage from this point to this 0, so this is nothing but voltage from upper trigger point to 0. So till that also the output will be in negative saturation. That means it will come from positive peak and then 0, and then it will come reach to up to minus 7 volts. So during this time, so you are going to increase the input in a negative way. So since the input is inverting during the negative cycle, so till it reaches the lower trigger point, so the output will be in negative saturation as well. So output will be in negative saturation, and output will be in negative saturation. And whenever the input just become equal to the non-inverting terminal of minus 7 volts, so it is going to switch from negative saturation to positive saturation. So that is the trigger voltage. So again it will be enter into the positive saturation, and during the rest of the input to in the negative peak, so you can see as you increase the it will switch to this one, right? So as you increase the inverting input voltage in the negative way, so output will be in the positive saturation itself. And when it reaches greater than till it reaches the input voltage greater than plus 7 volts, so the output will be in positive saturation itself. So this is what the hysteresis curve for this inverting Schmitt Trigger circuit, as it is mentioned. So this is nothing but hysteresis voltage. So this whenever they ask in exam, so you have to write this waveforms, input waveform, output waveform, as well as hysteresis voltage, and you have to explain about the operation of this hysteresis curve. And now if you consider the hysteresis voltage, so this is nothing but lower trigger point, this is upper trigger point voltage. So now hysteresis for this corresponding voltage is so it is difference of upper trigger point and lower trigger point. So that is the hysteresis voltage. So what is the voltage? So VUT minus of VLT. Suppose this is 7 volts and for upper trigger point, and minus 7 volts for the lower trigger point, means hysteresis is 14 volts. So 7 minus of minus 7, so that is 14 volts. Sorry, minus 7. So this hysteresis is having different. So we are not going to consider this lower trigger point. So it will be we are going to take it as a magnitude only. So hysteresis voltage means 14 volts, but hysteresis curve. What is the hysteresis curve? So you will be having 7 minus 7. So you will be having 0. So that is the hysteresis is located across the 0 reference voltage. So this is what you are going to get. So you can see the hysteresis is located exactly at the center. So if it is the hysteresis curve, if it is moved towards the right side, then it is called as a positive hysteresis. If the hysteresis curve is located towards the left side, means if it is moved towards the left side, means then it will be called as a negative hysteresis. Okay, so that is also possible. So based upon the value of the R1 and R2, which is going to imply for the non-inverting terminal. So this is about the zero hysteresis curve. So this is for the this is a 0 hysteresis, and the positive hysteresis is also negative hysteresis also. So hysteresis voltage means VUT minus VLT. So in the numerical and all, they may ask so this inverting design inverting schematic circuit to have a positive trigger voltage or upper trigger point voltage to this value and a negative trigger point voltage to be this value means you should design the circuit. So how you are going to design the circuit? So this is what you are going to design the circuit. So the figures threshold voltage are obtained using the voltage divider across the R1 and R2. So that is correct, right? So output will get divided across the R1 and R2 resistor, and hence that voltage divider resistor R1 and R2, the voltage drop across R1 is fed back to the non-inverting input, right? So that is what he has mentioned over here. Whenever the voltage across R1 is fed back to the non-inverting, so it is nothing but a positive feedback, and the voltage across R1 is going to act like the variable reference threshold voltage. Because variable, why it is called variable? Because sometimes the voltage will be positive and at some time it will be negative. So that is what variable reference threshold voltage, and depends upon the value and the polarity of the output voltage. So value is nothing but whether it is a positive value or negative value. So that is what it is going to depend upon the output voltage. Suppose if the output is positively saturated, the voltage across R1 is the upper threshold voltage point. So that is upper threshold point or upper trigger point. So VUT. In some of the textbooks, they used to mention it as a threshold point, threshold voltage, or in some of the textbooks they are going to refer it as a trigger point voltage. Okay, so upper trigger point. So this is going to be called it as a upper trigger point also, or else upper threshold voltage also. So there is no different meaning. So you have to understand. So that is trigger means what? So trigger means it is going to cause the pump to switch from one saturation to another saturation. So threshold is also going to work with the same. So only the difference is so we have to remember, so whether it is a trigger or threshold, so both are same, so the operation is going to remain same. So the input voltage V must be slightly more positive so than the VUT. So if it is greater than VUT, then obviously the output will cause to switch from positive saturation to negative saturation. So that is what. So as long as the input voltage is less than upper trigger point voltage or upper threshold point voltage, then the output will be in positive saturation. And whenever the input voltage just exceeds the upper trigger point voltage, so you will be having the output to switch from positive to negative saturation. And this is the upper threshold voltage. So we need to design the circuit. Okay, so when you are designing the circuit, so in the numerical problems and all, they used to give so upper trigger point voltage, so to be given is some voltage, so 7 volts or 8 volts or 4 volts or 2.5, so whatever the voltage they give, so to design the inverting Schmitt trigger circuit and all, so you have to put the value of this over here, and you have to see to make sure that what is the maximum positive saturation or negative saturation. By using this, you are going to design the value of R1 as well as R2 resistor. So VUT will be given, VLT, so lower trigger point voltage also will be given. So based upon upper trigger as well as lower trigger point voltage, so you are going to design the circuit of the resistance R1 and R2. That is a potential divider resistance R1 and R2. So on the other hand, so the output voltage will be in a negative saturation. So whenever the output is in negative saturation, so voltage across R1 will be referred to as a lower threshold voltage, or it is also called as lower trigger point. So whenever the V is less than this lower trigger point, the output will be in negative saturation as well. Whenever the input exceeds whenever the input exceeds greater than this lower trigger point, so the output will switch from negative to positive saturation. So this is what we have seen in the hysteresis also, the same thing. So only thing is that how you are going to design. So when you are going to design, so output voltage will be in negative saturation at that time. So we have to take that as a reference voltage for this lower trigger point. So upper trigger will be positive and lower trigger point will be negative reference voltage will be getting. So if the both if the threshold voltage VUT and VAT are made larger than the input noise voltage, the positive feedback will eliminate the noise output transition. So the false output transition. So that means it is so upper trigger and lower trigger point cannot be given greater than this except threshold voltage, as well as it cannot be given greater than the maximum power supply voltage or maximum output voltage swing. So we cannot give. So you should be within the limit. So based upon that, you are going to design the Schmitt Trigger circuit. So the output of the Schmitt Trigger is always square wave because it is a positive feedback. So positive feedback or open loop amplifier. So you'll be getting irrespective of the input signal waveform. So the output will be positive. And we can give. So as I told, Schmitt Trigger is used in triangular wave, so sawtooth wave generators, or in any case. So Schmitt Trigger can be used for triangular to rectangular, rectangular to square. Like that, you can used for generating the square waveform. Okay, so in any type of waveform, so you'll be getting output as square. So irrespective of whether it is a triangular wave or sawtooth wave. So sawtooth or a so it can be triangular or sawtooth or ramp or triangular. So any type of input, so output will be square. So when the input is a triangular wave, the output of the Schmitt is square wave. So whereas even if the input is a sawtooth wave, the output is a pulse waveform. So pulse waveform is going to square wave waveform only. So this is how it is going to get for the Schmitt Trigger, and it is very important thing. So any type of input, so you're going to get a square. So some part only. So you're going to, it is required to generate sine wave to square wave means you can go for Schmitt Trigger. Okay. So now coming to the comparator. So whenever the comparator, so it is also going to act like a special case of Schmitt Trigger is nothing but a special case of comparator circuit. So the comparator with the positive feedback is said to be excited hysteresis. So already we have seen in the 0% detector also. So whenever the input signal crosses 0, that is from positive to negative or negative to positive signal, whenever input signal is going to cross that 0 reference line, so output will get switched from one saturation voltage to another saturation voltage. So that is what we are going to get for the square waveform output. So the same thing we are also going to get for upper trigger point to the lower trigger point. In the case will be 0 only. So upper trigger point as well as lower trigger point for a 0 crossing detector is so 0. So whether it is a VUT or VLT is specified. So it is going to have a 0. So hysteresis is nothing but so whenever the input comparator exceeds VUT, its output switches from this one reverts the original state from positive to negative, and hence you will be getting the difference between the upper trigger and lower trigger point is called as a hysteresis. Therefore, V hysteresis will be equal to VUT minus VLT. So VUT is the remote. I have obtained the design part. So VUT is the remote part. So V sat into R1 divided by R1 plus R2 minus of V sat into R1 divided by R1 plus R2. So we are going to take it as a common R1 divided by R1 plus R2 plus V sat minus of minus V sat. So we will be getting. So this is about the hysteresis voltage. So this is about the numerical problem for the designing of inverting Schmitt Trigger circuit. So in the given circuit, so as soon as given in the inverting Schmitt Trigger circuit, so you have to write so the resistance R1 and R2 through which you are going to apply the feedback to the non-inverting terminal, and for the inverting input terminal you are going to connect the source. So in this he has given the resistance value of R1 is equal to 100, R2 is equal to 56 kilo ohm he has given. So input voltage is 1 volt peak to peak sine wave. So 1 volt peak to peak sine wave andre no. So 0.5 input during the positive half cycle and negative 0.50. Negative 0.5 is during the negative half cycle. So that gives a 1 volt peak to peak sine wave of the op amp. With the supply voltage he has given as what? So plus or minus 15 volts supply, and determine the threshold voltage for upper trigger point and lower trigger point, and draw the output waveform as asked. So he is asked for the VUT and VLT. So VUT, you know, so what is VUT? So VUT is nothing but maximum output voltage is 1 volt less than the maximum power supply. So plus or minus 15 means plus 14 will be getting. And what is the resistance R1? So R1 is 100, and into multiply with R1 plus R2, so 56K plus 100, so 56.1K. So we'll be getting, so this is nothing but 25 millivolts as the upper trigger point voltage, and minus 25 millivolts is considered as the lower trigger point voltage. So this numerical is only given as an example for this circuit. Okay. So this is what plus 25 millivolts and minus 25 millivolts. So this is only you need to plot. So this is the given input signal. So 0.5 1 volt peak to peak. So it is maximum positive peak is 0.5 volt and negative peak is minus 0.5 volt, and hence 0.5 LA, 25 millivolts in 0.25 volts. So that is going to have this one. So this is 0.25 millivolts. That is the upper trigger point voltage, and minus 0.25 volt is the lower trigger point voltage. And then output, if you solve, the hysteresis will be equal to 25 minus of minus 25, that will be equal to hysteresis equal to 50 millivolts respectively. So this is what you are going to get from hysteresis for the given problem. So any doubt in this? In the next class, I will just finish it off for the fourth module. So only one topic, instrumentation amplifier, is pending. So which I will be doing in the next class. Okay. So if I complete that, so I will be getting the fourth module will get completed. So is it clear? So this is about the module.
Yes, sir.
So this compared to first, second, third module, so fourth and fifth module you will be getting easy. So comparatively easy you will be feeling because operational amplifier fundamentals and all. So this is and moreover this topic, fourth and fifth module topic is not that much difficult, so that you can score more. Suppose if there is a open choice question pattern in a code, so I'm not sure so whether they will change or not. So if they give open choice question format, so fourth module, fifth module in the very correct without leaving one single application. So application numericals in ಎಲ್ಲದನ್ನು clean ಓದ್ಕೊಂಡ್ರೆ you can score 80 marks from the fourth module and fifth module itself. So are you aware of that open choice question?
Yes, sir.
Have you people discussed with you people? So VTU has given open choice question.
Yes, sir. Open choice, sir.
Open choice. So for your semester also it is applicable, I think.
How is it applicable, sir?
Applicable. So in order to boost up your, we can easily boost up. So this is very good opportunity. Even the tough subjects are there in this semester. So try to concentrate more which you are very comfortable and which you are going to solve. Okay, not only in my subject, so in every subject also you target for 3 modules, so best 3 modules you target. So I'm not telling to leave another 2 modules. Okay, so best 3 modules correct ಓದ್ಕೊಂಡ್ರೆ, so if you plan properly now itself, so this for this third IA, so third IA again you plan ಮಾಡ್ಕೊಂಡ್ರೆ, anyhow I'm going to give the topic with the fourth module and fifth module itself, right? So ಈ fourth ಮತ್ತು fifth module clean ಆಗಿ target ಮಾಡ್ಕೊಂಡ್ರೆ you can score 80 marks. Okay, 20 20 20 20. So 4 questions you can, they'll be given with the 10 questions. So 4 questions from the last 4 question only you can be able to attempt. Is it clear? So this is going to be very easy, as well as you can score more. Okay, so even if the previous semester score agilla andru third sem alli, so this semester you can boost up your marks. Okay, this is a now only I'm telling. So since it is open choice question, so you can score well. Try to plan. So not you should know when it is open choice means you should not leave one single question also. So single topic also you must not leave, and you should concentrate and you should score. Okay, so this is about the today's class. Okay, thank you. Then I will just wind up today's class. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.